In this video we're going to talk about working with binary and hexadecimal numbers. Now, the first time people see binary and hexadecimal numbers they can seem totally irrational. In this video I'm simply going to explain how they work and how the exact same logic that we apply to everyday numbers really still applies. So everyday numbers we should really call base 10. Okay, and when we're notating these numbers we use 10 different symbols. Now these symbols are of course each numbers in their own right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then of course we all know the next number is 10, but to write it down we have to use more than one of these symbols. We don't have a symbol for 10, so we sort of roll back all the way to 0 after 9. We put down a 0 and then a 1 goes in front of it, and we all know, even though we don't necessarily think about it, that this 1 is now worth 10 times as much as it would have been in this position. So that is actually 1 times 10 and 0 lots of 1. So the next number, 11, is exactly the same thing. 1 lot of 10 and 1 lot of 1, and so on and so on and so on. We get to 99 and exactly the same thing happens again. We have to roll over both these to zeros and put a 1 down in front of it, which is worth 10 times as much as if it had been there, which is worth 10 times as much as if it had been there. And we've got hundreds, tens and units now. Binary uses 2 symbols. Things with bi in them normally mean 2. Bicycle has 2 wheels, for instance. So we only use the 1 and the 0 to count with. So if we're counting, we start, or we can say 0 is 0. 1 is still 1. And how do we write 2? Because we've run out of symbols already. And exactly the same thing happens. We have to roll over to 0 and put a 1 in front of it. And of course that number looks like 10. It isn't 10. Obeying exactly the same rules, because we've run out after only 2 symbols, this must now be worth twice as much as if it was in that position. So that's 1 lot of 2 and 0 lots of 1. And then of course it's going to look like 11, but it's really 1 lot of 2 and 1 lot of 1, so it's 3. And then we're in trouble again because we can't write down the number 4, so exactly the same thing happens to get again, and it looks like the number 100. This 1 is worth twice as much as if it were there, which is worth twice as much as if it were there, so we're now 1 lot of 4, 0 lots of 1, sorry, 2, and 0 lots of 1. And, you know, again, 5, 4 and a 1, 6, 4, a 2 but not a 1, 7, 4, a 2 and a 1. Oops, sorry. And it keeps on going. We've of course got to 8, which looks like 1,000, which of course it isn't. Now hexadecimal is sort of the other way. Instead of using fewer symbols to write down numbers, we use more. So we still have our familiar and then we have 6 more symbols which look like letters of the alphabet. They are letters of the alphabet. And so, sorry, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 can be represented with a single character. Now, just like with base 10 numbers and with binary numbers, we get to a point where we can't write the next number using a single symbol. So this is 15. And to write 16, we do exactly the same thing as we've done with every other numbering system we've discussed. We have to roll back all the way to our 0 and lay down a 1 in front of it. So this is worth 16 times as much as it would have been if it were in this position. So it's 1 lot of 16 and 0 lots of 1. And it carries on, so that is 16, 17 looks like 11, 18 looks like 12, 19 looks like 13, and so on until we get to a number that looks like this, which is 255 in base 10. It is exactly the same logic as with all the other, with base 10 numbers and base 2 numbers. So I could write down a number like this, and if you see that number, you assume 33. And you must assume 33 if you haven't been told otherwise. But if I tell you that this is hex, and I can do that by putting 0x in front of it, you now know that these are units, and this is worth 16 times as much as this position. So it is 3 lots of 16 and 3 lots of 1. So it's of course 48, 49, 50, 51 in base 10. Now that really does look odd when you're not used to it, because of course the number 51 has neither a 5 nor a 1 in it, but that all is down to, you know, linguistics and the way we've learned to count since childhood. It is 51 if you obey the principles described in this video, and hopefully that has gone some way to explain why these 3 different counting systems, although they all look completely different, they are all logical in their way. Now there's an interesting relationship between binary numbers, or base 2, and hexadecimal numbers, or base 16. If we think about it, 16 and 2 are related. 2 to the power of 4, in fact, equals 16. What this means is that every 4 digits in binary can be represented by just 1 digit in hex. So 1, 2, 3, 4. This number is actually 15 in decimal. We've got 1s, 2s, 4s and 8s. 8 plus 4 plus 2 plus 1 is 15. And of course we can write that down in a single character in hexadecimal, so F is also 15. Now we can't write a bigger number than 15 using just these 4, and we can't write a number bigger than 15 using just a single place in hex. Where this becomes significant is we could do something like this. If I put down something like AB1F. Now, each position, we know these are 1s, these must be worth 16 times as much. 16 times as much again as 16 is 256, and 16 times again is 4096. So we've got 4096s, 256s, 16s, and 1s there at the end. This number, therefore, A being 10, we know the A alone in this position is 40,960. So this is a massive number. What this relationship between binary and hex means is that we can convert this number to, in this case it would be 16 bits, binary, without ever knowing what the number really is in decimal. And we can do this in a very, very easy way. We can pretend that it is simply 10, 11, 1 and 15 as if they were separate numbers. So we write down the 10, which in binary is like that, 8 and 2. We write down 11, 1011. We write down 1. Now we must put in the leading zeros. We must always put down 4 characters, and then we put down the F. And this number, in this case, we know that that 1 there, an incredibly large number, but we don't care because we can treat these as 4 separate numbers and then just sort of stitch them all together. So both these numbers are well over 40,000, and in fact the biggest number we could write, so F, 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 well, 2 to the power of 16, because this would be equal to 16 bits, is 65,536. So FFFF, or a row of 16 ones in binary, would be equal to 65,530, well, 5, because we start at 0. But we've managed to write down this number without ever bothering to do a conversion between this in hex and base 10 or decimal. And it might even be the case that doing such a conversion would be a fruitless endeavour. To convert either with decimal back and forth is slightly more difficult than this and will be the topic of another video. So I'm going to leave it there. I think we've covered quite a lot, and I'll talk to you in a future video.